Welcome to Lecture 12. Last time we introduced the idea of gravitational potential energy and elastic potential energy. And we connected these things back to the concept of work that we had discussed before. And we said that if conservative forces are the type of forces that are at work here, then the net work done by those forces is going to be equal to the negative change of potential energy. And we also added that according to the work energy theorem, the net work is also equal to the change of kinetic energy. So putting these two together, that means that the kinetic energy change plus the potential energy change should be equal to zero. And since we've defined mechanical energy as the total of the kinetic and the potential energy together, that means that essentially if only conservative forces are at work on a system, we don't have any external forces at work here, then the change of the mechanical energy from initial to final state should be equal to zero. This is what we would call, as I mentioned last time, conservation of mechanical energy. And we're going to meet other conservation laws as we go through this course, but this is the first one. And what it essentially means is that the kinetic energy plus the potential energy in the initial state has to equal the kinetic plus the potential energy in the final state. And again, this is when we have conservative forces at work and the system is isolated. If, on the other hand, we have forces that are external to the system doing work, we can still account for that. There could be a change of energy in that case, but then that change of energy has to be equal to the work that's being done by those external forces. So we can just incorporate that into our conservation of mechanical energy equation, as you see here. That external work can include such things as non-conservative forces like friction. So, to summarize then, we introduced energy first by talking about the energy of motion, kinetic energy, and the more quickly an object is moving, the more kinetic energy it has. And then we introduced potential energy, both gravitational and spring. There are other kinds of potential energy that exist, so this is not an exhaustive list, but that's the kinds that we're going to encounter in this class. We defined total mechanical energy as being the total of potential plus kinetic energy, and then we said that by the law of conservation of mechanical energy, if you have no external forces and non-conservative forces at work, then the total mechanical energy will remain unchanged from initial to final states. Otherwise, if there is work being done by external forces, then that work has to be equal to whatever change of energy took place. Okay, so with these ideas, I want to do several examples in which we apply conservation of energy to different situations. So let's go back to an example that we looked at last time where we were looking at the potential energy involved in pulling the plunger on a pinball machine. So just to refresh your memory, last time we concluded, based on Hooke's law, that the force that this child applied to compress the spring was 6 newtons, and that the work that the child did based on the elastic potential energy change was going to be 0.18 joules. And we decided that the final speed that this pinball would be traveling at was 2.1 meters per second. So go ahead back to the previous lecture if you need to review how we came up with those numbers, but we're going to move forward and ask a slightly different question here. So let's suppose that we had a way of finding what the final vertical height difference was that the pinball traveled up the ramp of the pinball machine before it came to a rest. So draw a little picture of this. Suppose that the plane of your pinball machine looked something like this at some angle theta, and you were able to determine that the ball went this high before it came to an instantaneous rest, after which it's going to head back down the ramp, and you were able to determine that this vertical height difference here was equal to 0.2 meters. And what we want to know then is when it gets to that height, what is its gravitational potential energy? So for that, we're going to use the equation we discussed last time, where we take the weight and we multiply by the height. Plugging in the mass of the pinball, little g, and this height, 0.2 meters, it's easy to determine then that the potential energy when it reaches that point is 0.157 joules. So this should give us a little bit of a red flag, because if we go back to the previous slide, we know that the child performed work which was equal to 0.18 joules, yet when the pinball reaches the top of this ramp, it only has 0.157 joules. So something must have happened to that energy. It can't just disappear. What could have happened is that friction, an external force, a non-conservative force, could have done work on that pinball as it rolls up the ramp. So to review then, the initial potential energy that the ball started with was going to be equal to 0.18 joules, but after it travels up the ramp and reaches the top of the ramp, its potential energy is only 0.1568 joules. So if we think about what's happening here, in the initial state, the initial mechanical energy consisted only of this elastic potential energy because the ball was at rest, and it was equal to this 0.18 joules. Somewhere while it's traveling along the ramp, it's got some combination of potential gravitational energy, the higher it goes, plus kinetic energy as it's moving. But when it reaches its highest point, it's instantaneously at rest, which means its kinetic energy, which is 1/2 mv squared, is also going to be equal to 0. Which means that in the final state here, the only energy, mechanical energy that I have present is that due to gravity, and that's my 0.1568 joules. Okay, so that means that work must have been done. It must have been the case that the work of friction accounts for this energy difference, and that work should just be the difference of these two. So 0.023 joules of work must have been done by friction. So the work of friction then is going to be the force of friction, kinetic friction that is in this case since it's moving, times the distance that the ball traveled. Now we know the vertical height was 0.2 meters, but the actual distance along the ramp is given here as 1.5 meters. Okay, so we need to then figure out what is the force of friction. Well, I know that it's mu k times the normal force, and if I recall from my inclined plane problems what the normal force is for an inclined plane, surely we could go back through that analysis using Newton's laws if we wished, but maybe by now you remember that this is mg cosine theta. So that's the force of friction at work here. We just need to multiply that by the distance in order to determine the work. But that is already known. We already know what the work is. What we really want to know is what was that coefficient of friction which caused this amount of work to be done. So I want to solve this equation for mu k. That is the only unknown that I have here. I'm going to take the work done by friction and I'm going to divide it by mg cosine theta times d. When I plug in the values there, I should find that the coefficient of kinetic friction is 0.2. Okay, so that's one example of utilizing the concept of conservation of mechanical energy in order to figure out some things that we may have been able to figure out in different ways when we were using Newton's laws. Okay, so let's now take a look at another example in which we are looking at somebody who's grabbing hold of a rope swing and going into the water. That might seem like a refreshing activity on a hot summer day like today. So we want to know two things about this particular scenario. One, we want to know the angle that the rope makes with the vertical when the person lets go. And we also want to know what the tension on the rope is at that point in time. So I'm going to draw a sketch of the situation to just flesh it out a little bit more. You start off with the person essentially going horizontally with their initial velocity, and then when they let go, it tells us that the velocity at this point is equal to 0. Okay, and at that point, the rope has gone through some angle theta that brings the person to that point where the velocity equals to 0. So let's take a look at part A to start with. In order to analyze this in terms of energy, we want to know which of the things in our mechanical conservation of mechanical energy equation we can set equal to 0. We surely cannot set the initial kinetic energy equal to 0 because the person is definitely moving. However, in the final state where the person is moving at 0 meters per second, then the kinetic energy will be equal to 0. Now, what about the potential energy? This person has a different gravitational potential energy in the final state compared to the initial state. So one of these two we can set equal to 0. In actuality, we want to do that where it's convenient. We could set the initial potential energy equal to 0. In other words, let's call this H equal to 0 at that position, or we could call this position H equal to 0, in which case this is going to be some negative number here, right? So oftentimes it's good to take the lowest position that the person is and call that H equal to 0. So the lowest position in the motion. So that's the choice we're going to make, but just bear in mind that that is a choice, right? We're just looking at where to define H equal to 0 or Y equal to 0 if you want to talk about it in terms of an XY coordinate system. So then if I call this first one equal to 0, then the second one is not equal to 0, and vice versa. So the correct answer here then is more than one of the above. When I write out the conservation of mechanical energy equation, where the total of the kinetic and potential energy in the initial state equals the total of the kinetic and potential energy in the final state, this equation will actually simplify because of what we just deduced above. The initial potential energy I'm going to set equal to 0, and the final kinetic energy is by definition 0. So now I've just got that 1/2 mv initial squared equals mgy final. But what am I trying to solve for? Let's step back for a minute and ask that question. Well, I want to know something about the angle that the rope makes. And so far, nothing in this equation is telling me anything about the angle. But actually, how high up you go is going to depend upon this angle. So we need to relate this y to the theta somehow. There's some geometry happening here. And so let's analyze what's actually going on. If in the initial situation you have the length of the rope going like this is L, then later on you still have the same length of rope, L, but we can think about this as creating a right triangle with the initial L that we started with. And this side of the triangle then is going to be the hypotenuse L times cosine of this angle theta, since it's adjacent to that angle. And then this little bit left over is this whole length L minus this part of the right triangle. so the whole length L minus L cosine theta, is actually the height that I've gone, y final. Okay, so if you can accept that kind of argument, by the way, this sort of geometry comes up a lot in swing situations or other kinds of situations in which you have a length here equal to a length there at some angle. So this sort of trick can be useful. Once I can relate now this y to theta, I can replace the y in my equation. So, oops, I'm going a little too far. Sorry about that. My iPad is not moving. There we go. So, as I was saying, we're going to replace the y with what I've just discovered in analyzing the geometry. And that is, instead of y, I can write this as the length minus the length times cosine of theta. So this is my y final that I've replaced in here. Notice that the masses cancel. Anytime I have only conservative forces at work here, it's usually the case that the mass is going to end up canceling. And that'll be a nice simplification. Once I solve for theta, combining all my like terms and isolating to solve for theta, and plugging in my values, I should find that theta is going to equal 40 degrees. So that answers part A of our problem. Now we want to move on to part B. In part B, we're being asked about the tension in the rope. So that harkens back to the things that we learned already with Newton's laws. So let's start by drawing a free body diagram of what the forces are on this person at the moment that he or she lets go of the rope. So at that moment, you've got the weight force on the person and you've got the tension force. Okay, and what is the motion actually doing? Well, it's sort of tracing out an arc. So I can think about this in terms of actually a centripetal force. And the centripetal force is associated with centripetal acceleration. However, we know that centripetal acceleration is equal to v squared over r. And at that moment, the person's velocity is equal to 0, which means that the centripetal acceleration must be 0. How is that possible? Well, there's something then that must be balancing this center-seeking force in the opposite direction to cancel it out and give me acceleration equal to 0. What that is a component of the weight force, which is along the same line as this towards the center, but it's pointing away from the center. So when I total up my forces in the centripetal direction, then I can conclude that this tension force must be balanced and equal then to the weight force in the opposite direction, mg cos theta. And so whenever I plug in then mg and cosine theta, I get a value of 525 newtons for the tension in the rope. Okay, so to solve this problem, we needed to use conservation of mechanical energy for part A, but then we had to go back to our ideas of Newton's laws for part B. So it's important to think about when we want to use energy and when we want to use a force analysis. With energy, we don't have to worry about directionality and vector decomposition as much because we are looking at scalar quantities. The energy involved in potential energy and kinetic energy are both scalar quantities. But if we're using forces, then we do have to think about these directions. The advantage here is that we were able to do this relatively straightforwardly in thinking about centripetal force. So let's do one more example where in this example we're going to think about a different question, not whether forces or energy is what we should use, but how we want to define our system. So let's suppose we have some elevator which is initially at rest and begins to fall when the cable breaks. After it falls a certain length, experiencing some friction. It will also have some safety measures so that nobody gets hurt in this experiment or this particular problem. What we want to know though is what the speed is of the elevator when it reaches the spring, and this is part A of the problem. So we're going to use conservation of mechanical energy here, but there are two different options for how we could define our systems. So we could define the system to just be the elevator and ignore the earth. We'll consider gravity then to be an external force along with the force of friction. In this approach, we're going to be able to use the work kinetic energy theorem to relate the work done by those forces to the change of kinetic energy of the elevator. The second possibility is to define our system to include the earth along with the elevator. And in that case, the external force is just friction. And when we use the equation for conservation of mechanical energy, the work done by friction will be equal to the total change of mechanical energy of the system. So let's look at how to solve using either of these approaches based upon how we defined our system. So with the first approach, where the elevator is the system and friction and gravity are external, then the work that those two forces do is going to be related to the change of kinetic energy. So the work done by gravity will be the force of gravity times the height difference. This work is positive work because the displacement is in the same direction that the force is being applied, i.e. down. The work done by friction, on the other hand, will oppose this, and it gets a minus sign because it is working in the upward direction while the elevator is displaced down. Those two forms of work together make the net work on the elevator, and that's going to be equal to our change of kinetic energy. Now in the initial state, there was no speed, so we really just have 1/2 mv final squared. And when we solve for that, we find a speed of 8.22 meters per second. Taking the second approach instead, where we define our system as including the earth and the elevator, then the external work that's being done is being done alone by friction. And so the change of mechanical energy, which is the change of kinetic plus the change of potential, will equal the work done by friction. And so the change of kinetic energy will be the same as before. This was equal to 0 to start with. And then the change of potential energy in this case is the change of gravitational potential energy that you see here. And we can likewise solve then for the final speed, and when you plug in the numbers or rearrange this equation, you can see that you will get the same answer, and that's encouraging because it should not depend upon how we define our system as to how the physics works. Okay, so finally, let's look at part B of this question, where we ask ourselves, all right, so we know how fast the elevator was traveling when it hits the spring. If the spring compresses by a certain amount in order to bring the elevator to rest, what must the value of that spring constant be in order for this to happen? So maybe we're designing a safety system where we consider this possibility and we want to know what kind of spring to use in order to make sure that it's able to stop the elevator in this 3 meters. So for this, we're going to define our system. Instead of looking at two options, I'm just going to give you one. Let's define our system as the elevator, the earth, and the spring. Okay, and then the work that was done based upon the friction is going to be equal then to this change of mechanical energy. And when we take that approach and we include the spring potential energy along with the potential energy due to gravity, and we simplify this, we can solve then for the spring constant K and determine its value to be what you see here. Okay, that concludes lecture 12. Next time we'll do just a few more examples with energy before we conclude this unit.